So I have uploaded some things to the Google Drive. It's mostly the same as what was up there, but for the first R session we're working on today, which is called R session 2, I realized there's a package that I hadn't put in the list at the top of the scripts to have you load it. And so there's another package so it's a very minor edit to the code, but if you have a moment, re-download the R session 2 folder and use the code from that folder. And also the R session 2 challenge, same thing there. Also, for the practical example 3, which is this afternoon, it's being led remotely by Julieta, who's in Argentina. She's going to be telling us a lot about growth curve analysis. She uploaded her slides last night as well. So those are on the Google Drive too, if you want to download them. Yeah, so just the entire R session 2 folder. I'll show you in just a moment. There's multiple things in there, and I'll help orient us a little bit. While people are downloading that again, now is also a good moment to remind everyone that recordings of the workshop are being made. And so I started posting them to YouTube yesterday because Zoom doesn't automatically put the captions on the recordings, which is a bit annoying. But on YouTube, you'll be able to enable closed captioning if you need it. And post-workshop updated scripts will be put on my GitHub. So this is the link here, just as a reminder, so you can come back and find it later. And in particular, for our session 2 today, which is what we're starting with, that might seem counterintuitive for those of you who didn't come yesterday afternoon, but that was our session 1. That was our sort of intro to R, refresher on how R works. So we're starting with our session 2. And in that session, we're going to go through quite a bit of code that can be sort of advanced. I'll try to simplify it and distill it down to the most important parts to understand. But I am planning in the future to make it even more user-friendly. So over the next year, I will actually push updates on this script. Maybe turn it into an R package or an R library. That would be nice and make it easier for a lot of people. But for today, you have my preliminary version of the script, and we're just gonna go through what it is. Should I wait another minute while people are... for those of you who walked in since I last said this, I did make some very minor edits to the R session 2 materials. So you might want to go to the Google Drive and re-download the entire R session 2 and R session 2 challenge folders. It's one line of code in each of these scripts. So if you don't want to re-download it, you can also I'll show you where in the code to add another line of code. I'm going to start going through the schedule for today. It's fine if you're still working on downloading things. This is just information about what to expect for the day. So we're starting with our session 2, which I'm calling data preparation. It's really like data preparation phase 1. This is my script, which I call a compiler, which I've been told by my husband, who is a real computer scientist, that I am misappropriating that word from computer science. that script, the aim of it, and this is what we're going to be working on in this session right now, is to take EyeLink's files and turn them into something intuitive, something that we understand, like what we would open up in an Excel file and be able to look at, or what we would open up as a data frame in R. So the entire purpose of this script is to take these, quite frankly, very ugly EyeLink files and turn them into something organized and pretty. And unfortunately, it's a bit of a headache to do this. So that's why we're going to take our time. We have a whole hour and a half. Hopefully we don't use the whole hour and a half. Hopefully we can go to coffee early. But we have lots of time to go through this script because it is complex. But I'm going to point out, for those of us who are newer R users, the most critical sections to understand, the sections that you would need to update for your future experiment. And the rest of it, you can just take on faith that it is doing the job it's supposed to. Then we'll have coffee and snacks. We'll come back for another session. This is phase 2 of data preparation. This is more so what you read about in methods of pupillometry papers. These are all of the steps you take to prepare pupil data, and these are pretty standardized steps. So we'll do outlier and blink exclusions. We will fill in missing data from blinking, because when we blink, our eyelid quite literally covers the pupil, so the eye tracker can't collect data. And so we'll talk quite a bit about that. We'll be using functions from the Gaze R package, and there is a copy of the paper, like the article about that package in the recommended readings. And it is a very nice walkthrough companion for that R package. That R package, it was in the installations list. So if you downloaded the pre-workshop folder, there was an R script that you could run to install all the packages you would need. Gaze R is a weird one because it's not on CRAN, that's C-R-A-N, that's the repository for R. So you have to download it from GitHub. So if you had issues with that, when we're at lunch in advance of our session 3, let me know. I've dealt with installing it because it's a weird one many times before, and so we can figure it out. There is lunch today. The lunch break is especially long in anticipation of if things go long, if people want to ask questions before we move on to the next session. There will be sandwiches, there will be chips, there will be sodas, and there are some cookies from my favorite bakery, Somos. Just was an opportunity for me to be like, support local and show off this great local bakery. So when we come back from lunch, more R. I know it's a lot of R today. This is like really like a big list of resources is what it's meant to be. And so hopefully this just gives you an idea of the resources that exist, so you'll know where they are and how to implement them yourself. In our session 4, it'll be a bit of an overview of all of the different options you have for analyzing data, as well as some of my opinions about what I think are the better options for analyzing data. But I'll show you the standards and what is used so that you can make an informed decision. We'll probably do a 5-minute break because Julieta is leading the practical example 3 remotely. So let me move this. I'll have to set up everything to show her in the auditorium. So if you want to attend in the auditorium, we will put it up on the screen in here, so you'll be able to see her present. BCBLians who prefer to go watch at your desk, totally fine. And she will be doing a deep dive on how to use growth curve analysis. This is essentially a way to do polynomial regression that reduces collinearity issues, long story short. Growth curve analysis is useful not just for pupillometry, it's being used for eye tracking now. Just lots of these different curve fitting methods are actually very applicable elsewhere outside of pupil research. So this session, I think she's done a really great job preparing it, and I really do highly recommend it. And then we'll have a social hour. So that's everything that's slated for the day. Please do join for the breaks and take part in the food. Are there any questions about today? Okay. I last night realized that I didn't have a section of this in my original slides, so I made this. Oh, thank you. Let me move those captions out of the way. For those who needed the intro to R, the R refresher yesterday afternoon, Marco led us through a lot of common R tools and packages and a lot of like basic R syntax. One thing that wasn't covered, and that's also a good refresher for anyone who wasn't here yesterday, is tidyverse. Tidyverse has sort of taken over the R world. There is a lot in tidyverse. It's like quite literally a whole collection of R packages that all share the same syntax. So like their style of how things are written. And one of the most iconic features in tidyverse, which you will see a lot in the scripts today, is called a pipe. And this is what a pipe looks like. It is the %, an arrow, followed by another %, no spaces altogether. This makes a pipe. Using pipes is really powerful and very efficient, which is part of the reason it comes up in a lot of the code today. So we can process files really, really quickly, as opposed to if you were writing something like a for loop or a while loop in R, it would take a really long time. These packages and these functions and pipes are just going to really help you efficiently process your data and summarize it. If you're familiar with Excel's pivot table function and how quickly you can get means of different things in your data, this is going to do the same thing for you in R. You can very quickly summarize things. There's a ton of things you can do with tidyverse and pipes. I'm not going to cover them all. I just wanted to make sure that I introduced this bit of syntax. So if you want to read more, I found a nice style guide at this link here. And I'll just show you a little bit of what pipes look like in action. So there is a data set that is built into R. You don't even need to load a library to view it, called Iris. And it's like a bunch of flower information, which is cute. And so this is me showing you the beginning. That's what the head function does. It shows you the first 6 rows of the Iris data set. And so we can see that we have, let's see, 5 columns here. We have information about sepal length, which I believe is the flower petals. Is that right? I actually don't know much about flowers. But length, width, and petals. So sepal must be something else. Who knows? Someone who knows more about flowers probably knows. And then species, which right now, because I'm only showing you the first 6 rows, it sort of looks like there are only Setosa species. But actually, if we look at this and we sort of summarize the levels of this column called species, it is a factor. It'll tell us, okay, there are 3 types of flowers in this data set: Setosa, versicolor, and virginica. What if we have this enormous data set in R? It's more than 6 rows. It keeps going. What if we very quickly wanted to know the mean of all of these columns with numbers in them for each of our species? The most efficient way to do this is going to be with a pipe. So the way pipes work is what we are doing here is we are taking the Iris data set. So this is a data frame in R. We are then applying a pipe. This is essentially a way to do procedurally a bunch of apply a bunch of functions onto this data set. So it does it one step at a time. The first step is we use this group by function and we say, okay, we know there are 3 types of species in there. Use those factor levels and group the data by those levels. So that's step number 1. Then we use another pipe. We're saying, okay, go apply another function. Here we use the summarize function. I use this all the time. And you can do many operations at once with the summarize function. And so here we are going to make a new column called sepal.length. And we are going to take the mean of the column that was sepal.length. So if I go back, Remember, we have four different columns here with numbers in them. And so we are saying, take that column, we're going to make a new column. We're keeping the same name. You could change the name of the column if you wanted. So I often will say sepal length mean as the new column name. And so you can see we're doing that for each of these. This last one is counting the number of species, which is sort of an uninteresting variable, because when we look at the data, it has created for us the summary of means. It's very quick. The way the code looks, and I think this is why Tidyverse has really taken off and it's like taken over the R world, because compared to base R, which is what we call all of the built-in functions in R, it can look very organized and pretty. So people are a big fan of it. You'll see a lot of pipes. Any questions about pipes and how that works, Marco?
So sometimes the functions are written in your packages, so you may have like this problem that this says that the function doesn't work. Like
Yep.
That. So you have to specify the other thing because it's
Yep.
overlapping, you have it right, and that will happen to you. Always have that.
Yeah, and actually we'll see, I'll try to remember to point that out in the R code that we're going to go through. Sometimes I have to say from the dplyr package, use the summarize function. And this is something that didn't used to be a problem. I don't know if something got pushed that made it a problem, but so sometimes you'll see we shouldn't need to call the packages every time we're running these functions, but I'll show you what that looks like. And so you can put that into your code for redundancy, essentially, so that you don't get errors thrown.
But sorry, but you have to load some libraries or packages to run this.
Yes, yeah. Yep, so we'll see the libraries you need to load at the top of the scripts. But if you're trying this out on your computer right now, you probably need dplyr. So
I found that sometimes on the LMR and LMR to have like some build functions that overlap with the name of the ones.
oh, okay.
So R gets crazy.
Yeah.
Know which functions get.
That would explain a lot of the annoyances that pop up in my scripts, because I'm often using LMER or LME4 package at the same time. Yeah. Okay, so that's pipes. The focus of this first session is going to be, let me actually quickly change my setup here. So I'm going to mirror. Okay. So close that and that. We're going to be going through, I have a PowerPoint here, but first what I want you to do is I want you to open our studio. And I'm gonna close what I had open before. When you open our studio, you shouldn't, unless you were previously using R, you shouldn't really have anything open here. If you navigate to where you have saved the files from the Google Drive. Oh, sorry, is someone saying something online? Okay, let's not worry about that. If you go to our session 2, we're in our session 2 right now. There are some options for you. So a little bit of context here. In R, there are different formats you can write your scripts in. The most basic one is .r. And so if you go to r_basic scripts, you can open up this file. It's the R session 2 ASC compiler.r. And what you'll see is just code. It's just code the whole way through. Should I zoom in a little bit on R? Or yeah, maybe I'll do a, okay. But there is a, I don't know, somewhat newer, maybe a decade old though, option called R Markdown. And some people prefer R Markdown. So I have provided both of these. They have the same code in them. I want to clarify that. They both have the same code, but in the R Markdown, what you will see is essentially code chunks, which are these gray areas surrounded by text. And this text is going to mostly line up with what I show you in the slides. And I've also labeled all of these code chunks. So as I go through the slides, like when I get to code chunk 2, you'll see that what I am showing you for code chunk 2 does indeed match up with code chunk 2. So that might be a little more intuitive for following along. And if you are using our Markdown, the other handy thing, if you're unfamiliar with it, is for a code chunk, you can come over here and click this play button, and it'll run everything in the chunk. If you prefer, instead, you can hold command and you can run things one line at a time. I like to run things one line at a time. If you're using the basic R script, I also recommend holding command and clicking enter to run one line at a time. Any questions? People able to open things up? So I was telling people, and I saw a couple people trickle in, so I'm just going to repeat this. I noticed last night that I didn't load a library that we need for the script at the top. So I did update the scripts in the R session 2. So you're welcome to download the R session 2 and R session 2 challenge folders, again, from the Google Drive. The only change that I made is right here. Here it's line 12. It's library Tibble. And if you go to run library Tibble and it yells at you and says, you don't have that package, it's quite easy to install. You can type install.packages, and then in quotes, you will type Tibble and you'll run that. If you already have it installed, you do not need to install it again. You only ever need to run the install packages function one time. You can check if you have it installed by going to your packages tab. Hit that. And you could scroll down. And in my case, I would see that I do indeed have Tibble, and it is also loaded because there's a check mark. All right. Okay, so you have your R script. You're ready to follow along. You're also welcome to not run things in R if that's your preference, but I do think it's great for learning purposes. What else is in this folder? Well, there is something called R Quarto, which I've put in parentheses slides. These are the slides I'm going to be showing. If you want to follow the slides, you can double click the .html and it'll open up what I have here. On my computer, it only lets me move side to side in the slides by using my arrow keys or using this sort of drop down to jump around. You don't need to open up anything else from this folder. So this is just how I made my slides. And then the last thing is some example data. So I want this to be a very practical and helpful workshop. So I'm giving you real data. We're processing real data, and we're going to do it together. And then after we go through a data set together, the R session 2 challenge is going to be a different data set. Well, you're going to have to change a little bit of the code in order to make this script work for a different data set. So application of what we're learning. I want to take a moment to explain what ASC files are, because the name of this session is compiling ASC files. So EyeLink, for reasons unclear, has their own file systems. So the file that gets generated when you run an eye tracking or pupillometry experiment is a .edf. That stands for EyeLink data file. Those files, I used to be able to load them into R with a special package, but that package stopped working. So long story short, EyeLink gives you a software. And so it's at BCBL, it's on all of our eye tracking computers. And it's called EDF to ASC converter. It's very easy. I promise you, it is completely intuitive. So what I have done is I have taken the EDF files and converted them to ASCs. This isn't to say that the .ascs are prettier or easier to work with than .edfs, but these are the two types of files that you can get from EyeLink. So the whole point of this script is going to be taking these ugly ASC files and turning them into pretty files that are going to appear in this folder. So let's get into it. This script is going to take our ASC files and it's going to extract critical information. This script does need customized for every unique project. And I was saying this at the beginning that I do have intentions in the next year of turning this into an R package and making it a little bit more foolproof so that it's less work because, and we shouldn't all have to become expert coders just to process our data. So we're going to go over in this section what parts of this script need customized. You do not need to understand every little detail of this script. It's basically just taking these files and converting them to a better format. So I will try to point out what to pay attention to. The data set, because I told you we're using real data. This is a preliminary data set. I've only given you 5 subjects of data because doing more than that would take more time than we have for this. The lead author from this data set, her name is Jimena. She just went back to where she's doing her master's thesis and she's writing her thesis right now, but she was here doing an internship for 4 months and she was collecting this data set and she did a really amazing job. And what she was looking at for this data set was language switching. And this is a perception experiment. I do a lot of stuff with speech perception. So all of our examples will be speech perception. And in the task, what participants do is every trial, they are shown on screen a list of options. These are Spanish Basque bilinguals here in Spain. And they are shown that they are either going to get a trial that goes Spanish to Spanish, because they're going to hear 2 sentences in a row. Or it could go from Spanish to Basque, Basque to Spanish, or Basque to Basque. These are the 4 possibilities. Technically, I'm giving you a subset of the data set. I'm not giving you the whole data set. So if it looks like this is, missing some other things, it's because it is. But in this data set, there was an arrow pointed for each trial at what type of trial they're going to get. They then clicked, because this is actually a button, and it would start their trial. They are listening to 2 sentences in a row while we track their pupil. And then in order just to confirm they are paying attention, they have to do a fill in the blank task. So these are the 2 sentences that they heard, and one of the words from one of these 2 sentences will be missing, and they have to type what the missing word is. So this is just to ensure that they're paying attention, and we aren't collecting data from that period. So that's the task. This is the data set you are going to be processing. And I already told you what an ASC file is, but here's just a reminder. There is an app that's on our eye tracking computers. And if you have an EyeLink system, they have given you the app that lets you convert from EDF to ASC. So now we can get started. So we are going to run code chunk 1. So if you're in R and you're using R Markdown, for example, you can just click this play button. And what you should see is in your environment, a couple of things will pop up. This is the first thing that you're going to need to edit because this is where we are setting up our directories. And this will not be correct for your computer because as we can see, this is pointing to Drew McLaughlin's computer, her Dropbox folder, and that is not where you have your files. So you need to figure out where you have your files saved. The way I do this, because it's quick and I am lazy, is I will often, I'm a Mac user, so keep this in mind. I will come here and I will copy the path, just like so, and paste it in. If you're on a PC, I think actually copying paths is honestly easier. And so, does anyone have any questions about getting their path? The other thing you can do is you can navigate through your file system in order to figure out where you are. And yesterday, Marco was showing us a wonderful thing with the tab button. So if you type set working directory, set WD, and then quotes, you can actually click tab and it'll pull up all of your folders and you can I can click on documents and then I can click tab again. Oh, and then, yeah. And then I can click, oh, I want to go into my Zoom folder, tab again, and so on. So there's lots of different ways to get your directory set up. Here, I am actually just loading. This is just a string of my directory, and I have named it ASC directory. And once I do that, it is in my environment. And so later, when we move to code chunk 2, or code chunk, a code chunk lower down, we'll be able to very quickly switch between directories. Any questions about that? If you're on a PC, your file paths are going to look different than they look on my laptop. PCs and Macs do things differently. Let's move on. Once you have your directory set, we can use the directory we just made and feed it into this function that will essentially look at your folder, and it'll get all of the paths to all of the files in this directory. And so if you run code chunk 2, you're going to see a couple of things pop up in your environment. The first is a vector of characters. So if we type all ASC file paths, it'll print down in our console if you want to take a look at them. And what you'll see is these long strings pointing to all 5 of the files. The other thing I did is I just got a count of how many files are in my directory. This is just a good confirmation. Okay, there are 5 files that it is detecting in this directory that all end with .asc. Let me know if I'm going too fast, but I'm just going to keep cruising until someone tells me otherwise. So what's code chunk number 3? Well, code chunk number 3 would actually be the entire thing. And let me explain what I mean by that, because obviously we aren't going to do the entire thing all at once. That wouldn't be very good for learning purposes. But the next chunk of code is a very large for loop. The reason it is a very large for loop, starting here with 4, is because this code is written to run on an entire directory. We want it to come through and run this code on every one of these files and convert every one of these files. So writing it as a for loop is convenient. When you go to actually run this on a data set, you will essentially click run on this file and it'll process all of anything you have put in this folder. It'll process and it'll spit out the cleaned up files into this folder. And it'll be chef's kiss, perfect. You'll be very happy. But for learning purposes, or anytime you're editing this script, it is much better to not just run this enormous for loop. We want to essentially enter this for loop, is what I like to call it, so that we can go through it line by line. So to do that, in order to progress line by line, in R, we're going to set the loop's variable equal to 1. This will allow us to go into the loop as if it's the first iteration of this loop. So to do that, you can run the next chunk of code, which is just assigning the number 1 to this underscore file. So a quick reminder of the syntax of for loops. For loops are set up with the word for. This is an R because it's different in every language, unfortunately. Then in parentheses, you have variable in a sequence, and then we have these curly brackets, and anything in the curly brackets is what you are doing, a long list of things typically, for every iteration of this loop. So when I say we're setting the variable equal to 1, we look at actually I'll go backwards. If we look at the start of the loop, I have named my variable for this loop, this file. That means on the first run through this loop, anytime this file pops up, which isn't too often, it'll be assigned to 1. When it comes through this loop the second time, it would assign this file to be 2. So this is just sort of how for loops work. So in R, I'm just going to run this code chunk that assigns this file to be 1. We can see it pop up in our environment on the right. And now I have broken in the RMD file everything into code chunks and labeled them 3A, 3B, and so on and so forth. If you're doing this in the base R, because that's your preference, what you'll want to do is in your console, set this file equal to 1, and then skip this line of code, and then you can start running 1 line at a time by hitting Command Enter within that for loop. So let's start talking about this code. We're going to seize this as a learning opportunity, even though it's a little bit boring. The first thing this code does in code chunk 3A is it pulls a function from the EyeLinker package. So this is a package that was in the installation. So if you get an error here, it's probably because you didn't install it. So let me know if you need help installing. What the EyeLinker package, this read.asc file does is it takes this ugly, messy ASC file, and it's going to turn it into a list with a whole bunch of information for us. And when I say list, what I mean is there are multiple layers. You can imagine multiple Excel files are being opened up all at once. So go ahead and run this chunk of code. It'll take a minute to load because the ASC file is quite large. Pretty much anytime you're doing eye tracking or pupillometry, the files end up pretty big. I mean,
a warning, not.
yes. Yeah, I've been getting that warning lately too. Yes. I'm going to message the EyeLinker people, but so far it hasn't prohibited me from processing data. So I'm not sure. It's something about the UTF encoding, but don't worry about it. From what I have seen, it still processes just fine. The next thing I like to do, so like I said, this data, if you look at it in R, it is a very large list. It says there are 8 elements. And so if you scroll down, you can see these are essentially 8 Excel files. And, oh, sorry, the raw is one of them. Then we have SACCADs, that's what SACC stands for. It's an enormous file with many different layers. And I like to free myself of this notation because I find it confusing. So what I like to do is I immediately grab the raw data and I assign it to what's called DF samples. And I do the same thing for the messages. These are the 2 layers that are the most important, essentially. And if you do that, you can then click on DF samples and take a look at it. What you're going to see is some really important information: timing, the X coordinate, the Y coordinate, and this is pupil size, which is exciting. Look at us. We already have our data open. How great is that? In the messages, so go ahead and click on messages after you've created it. You're going to see the thing that I dislike about EyeLink, which is this enormous, long, ugly list of messages. But this is all the important information that we need about our experiment. This is the whole point of this compiler. We're going to take this information and we're going to put it into a pretty file that's nice and organized for us. The first thing I like to do then is rename the DF samples. That stands for data frame samples and messages. And if you do that, you will see that I have renamed the column headers. The reason being, and I have a note here, is for whatever reason, EyeLink labels this leftmost column block when you first open it, but it's actually your trial. And so this is important. If you look at your messages and you scroll around, you're going to see a transition from 1 to 2. And you will notice, conveniently, right at the end of trial 1, a message was sent that says trial end. And what you will also notice is some important timing information, like this was the onset of our first sound. It's going to reoccur every trial. Does that make sense? Every trial, we have programmed our experiment to send these same messages. So every trial will have timing information about when the sounds were played. If you are showing pictures, you could have this message be something else. It could be picture 1 appears. This is something that you customize, something that Daphne and I mentioned yesterday. Sending messages to the eye tracker is a really critical part of programming your experiment. And this is the back end. So this is the product of your labor now. You have all of these messages telling you all sorts of information, including very custom information about this experiment. So in this experiment, like I said, we're going to play 2 sentences for the participant. And we're doing randomization across our participants. So this is the second trial for this participant. And I need to know what file was played for them. And so this is where I'm getting that information. So all of this is in a very long list in these messages. So we need to extract this information and make it a little more intuitive. Any questions so far? Okay. Let's move on to code chunk 3B. This is where we start extracting our critical messages with time points and trial information. I've separated this into two chunks. The first chunk is essentially the most important message. It's what's going to allow us to determine when this trial started. Because something important to note about EyeLink is if you look at your DF samples, this is just the raw data, you will notice at the very top of this data frame, time starts at 2,492,442. I do not know how EyeLink chooses to initialize their numbers, but it is different for every participant. And so the starting number is not meaningful. We need to know, using our messages, when the sound started. And we can see this time point, we're going to be able to match this up with this time column. Does that make sense? Because this is like a really important conceptual, like, groundstone. Okay. I'm seeing nodding. I'm going to take that as affirmation. So here I am using a function called grep. This is where you don't need to worry about exactly how the grep function works. All you need to know is I use this function to search the messages data frame for a specific string. It doesn't have to be the entire string. And in fact, it will not be the entire string. If you go to your messages, we're going to be searching for strings like file name 1 and ignoring all the junk around it. So the grep function is just a powerful string finder. It's going to find, it's going to look through this column of text and it's going to grab all of those strings. I then use that same exact function and I do the same thing for all of my experiment specific information. So this is where you would need to edit. So this is like, if your eyes are glazing over because this is a lot of R code, reasonable. This is what you would need to edit for your experiment because your experiment might not have 2 file names and so on and so forth. But you can see it's a very consistent set of code you can plug and place. If you have different messages, it's just, you know, instead of file name 1, rename it with your messages and just do that all throughout. Okay, so this is the #1 thing that you would need to edit. Go ahead and run this code chunk. And what I want you to observe is your environment here on the right should explode with lots of different data frames appearing. And the other thing I want you to observe is we're seeing a lot of 50 observations. And this is a good logic check point. There should be 50 observations for this data set because we had 48 trials and 2 practice trials, so 50 trials total. So that makes sense. And if you want to, go ahead and open up one of these and you will see all of the rows that contain whatever important string from your messages have been grabbed and brought together into one data frame. It's a really handy function. And we can look, for example, let's find something more interesting. If we open file name 1, for example, you'll see the order that the files for this experiment were presented because it's a randomized order. For every participant, this is going to be different. So we have grabbed our critical information. Hooray. Oh, one thing to note about the audio onset one. You'll notice there's a bit of a difference between file name 1, where we have critical information here in the text column on the right, and it's changing every trial, versus the audio onset. The text column isn't actually useful information. What we care about from this data frame is going to be the time column. This is our time point for when the trial started. The most important information, basically, in this file. All right, let's keep moving forward. Code chunk 3C. I'm going to close some things. Okay, code chunk 3C is going to look at, we have for this data set, not all data sets are going to be like this, but for this data set, I have one of my messages is the length of a trial, how long the duration was, because the trials varied in length a little bit. And so this next code chunk, what it's doing, it's going to come in and it's going to grab the numbers from the right of here. This is a really ugly long string, which is not good for processing things in R. So just take it on faith that this code is going to grab what I need and turn it into something that is actually usable. So now what you should see appear down here is a vector. And so we can type trial end time. And we have a bunch of times here. Okay, so essentially we have calculated how long each trial is. We know the start of the trial because we have those trial times, and we've calculated when the end of the trial is. We're gathering all of the relevant information. And then code chunk 3D is just to make it all clean and pretty. So go ahead and run 3D. And what you're going to see is a data frame, DF trial times, will appear. And go ahead and open DF trial times. This is where you see the fruits of your labor. We have 50 trials, good logic check here. And we have onset times and we have offset times. We can also do a quick sanity check. So we can take the trial end time and subtract the trial onset time and see what number we get. This is in milliseconds, so this is like a 12.5-second long trial. Correct, that is how long this trial was supposed to be. And so we're happy about that. Backing up, one other thing that's in this same code chunk is I'm extracting the subject ID. So if you remember, we got the long directories coming to these files. This is the automatic naming. You might have custom naming for your files, so this could of course be different, but this is just some quick code where I am telling it to look at this string and grab these first 5 characters, and it turns it into a subject ID, which you can see here, P_101. Beautiful, perfect. That's all the information we need. We don't actually care about what year their data was collected in, what time, so on and so forth. We just want their ID. So we have collected lots of important information now. And now that we have information about timing, we can grab the data. So we know when trials start, we know when trials end. And we have a big data frame with all of our samples, the X and Y coordinates and our diameter. Now we want to make a big file that's going to essentially, we don't want all of this data. We want to come in and extract the chunks that are our actual trials. So that's what the next chunk does. It is a while loop, which is fairly complex. Go ahead and run this. And what I want you to observe are the messages that are going to be printed out for you. Look how fast that was. Sorry, I'm very proud of that. I made this code more efficient in the last month. And this is a single participant. If you imagine a lot of my data sets have 50 participants, like less than 5 minutes to get this data. It used to be longer, but let's look at some key things. I'm going to go through this. It's fine if you want to let your eyes glaze over and not pay attention to the details here. But I do want to explain it just in case you want to come back to this recording and have a deeper understanding. So for a while loop, you always have to set a counter. So in this case, I'm using the current trial number as my counter. Essentially, this loop is going to go through and it's going to extract each trial one at a time. It is creating a big old list. Essentially, every trial is going to be a data frame, and you're going to have a list of 50 data frames. We enter our while loop, and the first thing we do is we set some Boolean statements and so on and so forth. These are true-false statements. This is how I create messages in this experiment. So you know how when I ran that, it was like, ooh, this trial was added to the data frame temporary. That's what dftemp stands for. That's what these are for. We go to our df trial times. We get the start of our trial. We then, this is an important little bit of code, we do some redundancy sort of stuff here. So the EyeLink can record at 1,000 hertz, 500 hertz, or 250 hertz. So depending on your data set, it might be recording at a different frequency. This code is written to work no matter which of those you are using. This is actually 1,000 hertz data that we are processing. But the other reason I have this in here, even if you're collecting at 1,000 hertz and you think, I don't need this, I don't need to check for 500 and 250 hertz. It's good to have this because sometimes the EyeLink does inexplicable things and it just won't have a time point. Or the bigger thing that used to happen, the EyeLink I used at my old institution, it collected at 500 hertz. I don't think it even could do 1,000. And for some subjects, it would start on odd numbers. And for other subjects, it would start on even numbers. And sometimes from one trial to the next, it would change. Yeah, I don't think the EyeLinks here have that problem, to be honest, but redundancy is good. So essentially, we have the start time for this current trial that we have collected. And then I have just said the time point after that, and the time point after that, and the time point after that. We're going to check for those two. The next chunk of code, what it does is it goes into that big samples file that has our X, Y, and pupil diameter. And it's going to look for our trial start time. And you can go ahead and open up time point row. This is what it's doing essentially. So because we collected at 1,000 hertz, this is our onset time for this trial. What it did is it found the row number for that trial. This is trial 50 because I ran the whole thing. So this is the last bit of information it collected. And we can see the X and Y and the dilation and so on and so forth. We can see it collected the next 3 time points. Since we have 1,000 hertz data, we don't need those time points. So the next thing the code does is it just takes the first of those time points. So this next thing is a Boolean check. This is checking to see, okay, did we find the trial start row? So this is a good point to clarify that, as I was saying before, sometimes EyeLink does inexplicable things. It'll drop a trial, things happen. And so sometimes it'll go, this code will go, it'll look, it'll be like, I was told that there should be a trial that starts at 2,500,000, whatever. And it'll go look for it and be like, that data doesn't exist. So that's what this is here for. It's like, was this found successfully? If it was, then it'll say true. And if not, it'll throw a whole bunch of error statements. It'll drop the trial. I'll show you what this looks like in just a moment. It'll be like, panic, nothing worked. I have some comments in here, which are essentially, if problem persists, check DF samples and DF trial times manually for logical error or data corruption. I have had occasions where the entire file is corrupted and things are weird and wonky and I have to throw out the subject. Not frequent, but it has happened. The other thing that is much more frequent is logical error, by which I mean you thought that this was the onset of your trial, every trial, but actually it wasn't. Is there a question before?
I was just wondering, I mean, if it's keeping like a time point,
Mhm.
it's recording at 100 hertz, for example,
Mhm.
then does it make sense? And if it's not doing it for all the trials, of course, I don't know, and that is like big problem with that participant. But if it's one trial, you can either throw it away and that's fine, I guess. But does it make sense to just look for the closest time point? Is that at the beginning of the trial, or is that
So it's a reasonable question. So that, just to repeat, the question was whether it makes sense to drop an entire trial if you're missing a time point. So what I will say about that is if we come back here where I was talking about we're collecting at 1,000 hertz, but we have redundancy here. If you're collecting at 1,000 hertz and a single time point is missing, it will still be able to get the entire trial. If you're missing all of the surrounding time points, then the trial is probably entirely missing due to data corruption or logical error. So, but a reasonable question for sure. I have at the bottom half of this, I want to note, if you're editing this for your experiment, you would want to customize this. This is me dropping from all possible data frames. There's probably a more efficient way to do this, but this is just me essentially saying this trial, there's something wrong with it. I'm getting rid of it everywhere. If you find the start of your trial, though, things are going well, and you want to find the end of your trial, this is the same code. It's looking for the trial end time, so we don't need to focus on it too much. And at the end, we have another Boolean statement where if it finds the end of your trial, it'll say, hooray. And if it didn't, it'll throw errors. And these warnings and messages are specific to the start or the end of the trial, and they will have information for you to help you figure out what went wrong, essentially. I want to show you, I'll come back to this. So we know what it looks like when things go smoothly. It ran this participant in like less than 5 seconds, and it was like, woo, trials 1 through 50 added to this data frame. What happens when it goes poorly? You aren't going to see those happy messages saying it's adding your trials. You're going to see things like this. So this is that chunk of code that I wrote. And so this is saying trial start time point, and it's going to print the value for you, was not found in your DF samples. So, and then it tells you what to do about it. I actually forced this error to occur. And so this is something I want you to try out just so you can see what I mean by a logical error. So if you go to the code and you come to line 165, if you're in the RMD, this is where we are going into DF trial times. And we're saying, okay, for this trial, this is my onset time. Okay, that's what this line of code is doing. It is grabbing the onset time. Go ahead and comment that out. And instead write trial start and type a random number. So I'm going to type 10. I know 10 does not exist in this data frame because as we saw when we were perusing, it starts at 2 million. So 10 is not going to be in there. So what this is going to do is for every trial, instead of grabbing the onset time, it's going to look for 10 as the onset time. This should cause an error. This is a logical mistake. And if you run it, we get a whole bunch of warnings. Notice that these warnings all say value equals 10. Now, when you actually make an error, that's something that's more so like all of your onset times are shifted by 1,000 milliseconds. And that's the error. Then it won't be the number 10 every time. It'll be unique numbers every time. And so you will have the information you need to search and figure out what went wrong. Any questions? I see ponderous eyes. This is a big chunk of code. It's extracting the data, and I think we can sort of leave it at that. I'm going to put this back. So if you forced it to make a mistake, put it back. And in fact, you might want to actually, if you forced it to make a mistake, clear things out and rerun the code because it's probably overwritten half of the file and we don't really want that. Okay, so that was code chunk 3E. It's the big one. This is me rerunning it correctly. It's collected 50 trials. Let's move on because this isn't the most exciting part of the workshop. The next thing we need to do is in code chunk 3F. This is where we essentially say where we want the 0 point of our trial to be. Because, for example, if you look at your data, what you're going to see, I think I have this on the next slide. The data we just extracted, time starts at all these crazy random numbers, and they're different across all trials. If you tried to plot this data, it would not do what you wanted it to do. And so what we're going to do is we are going to take our trial onset time and we are going to subtract it from all time points in that trial. What this does, you can see here, if our trial onset time is at this number ending in 448 and we subtract it from all time points, 0 will be our onset time. Does that make sense? The logic of this? So the next bit of code does this very efficiently. I have a few notes here about how for this trial, I wanted 1000 milliseconds before the onset. And so I have some adjustments here for that. And so you can customize this as you so desire. The next chunk of code is super ugly because it's in list notation, but I promise you doing things in list notation is very efficient. Let's talk about code chunk 3G. This is something you would want to customize. What it is doing is it is going in all of the information we extracted, like file names, so on and so forth, counterbalance. We're going to add this to our data frames because right now our data frames are just, they're just this. There are X, Y, and dilation, but we need to know what the trial was. We need to know what the condition was, what their response was, anything specific to our unique experiment. We want to add this to our final data frame so that we can actually interpret our data. So what this chunk is doing, this is chunk 3G on the bottom, and I have put the chunk 3B from up above in the script above it so we can look visually and compare. The exact same messages that I extracted at the top of the script that are custom for this experiment are down here. And so you can sort of look up and down and you'll see that it's the same stuff being put in here. This is really ugly, and I want to explain why it's so ugly. So if you recall, if we go open file name 1, a lot of the messages in EyeLink, the default is to have them look like this. It's !v trial var, this trial variable. You can technically customize this, but long story short, there's just like a bunch of junk in this text string. And what we really care about is the very end of this text string. This is what's defining trial 1. Trial 1, they heard file 61, which is a sentence. And so long story short, this very ugly code is extracting the bit of that I want. If you don't want to deal with the complicated code, you could have just told it to grab the entire string. This is just me cleaning things up as I go. So go ahead and run 3G. And then I like to think of 3H as freedom because we've been in list notation. List notation is not intuitive. It's really, I think, hard to wrap our brains around. And just to remind you, this what's called DF temp, that's data frame temporary. It's not a data frame, actually. It's 50 data frames in a list. Essentially, we have 50 Excel files, you can think of it. And we have a list of our 50 trials and all of their data. And you know what? We want all of this to be one file. And it'll go from trial 1 to trial 2, down, 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 down. And so this single line of code does that, which is pretty cool. So it takes this list and it's going to smash all of our trials together. It's using what's called the rbind, which is the row bind feature or function. So go ahead and run that. It might take a second, but then if you click on DF, get excited about what you're about to see because we actually have an intuitive data frame with everything we could possibly want for when we make plots, for when we create models, and so on and so forth. So that's the fun part after the long trudge through a lot of stuff. I then do some extra stuff here where, for example, I use from the dplyr package with a pipe. Pipes have come up officially. I'm using the select tool to grab columns. So for example, I don't like the order of columns. There's some columns here that I don't need, like lowercase trial versus uppercase trial. I don't need both of those. And so what I'm doing here is I'm grabbing the trials I want. This is also a good point to note that pupillometry and eye tracking data gets enormous. Not as big as fMRI, but it's still pretty big. And so if there are columns that you know for certain you are not going to analyze, you do not need to put them in the final data frame because it's adding additional dimensions, not dimensions, but it's extending the size of your data frame. And so this does add up in terms of space on your computer. When I'm running this on the server, it's been running so quick and so beautifully here on my laptop. When I run it on the server, it's so slow and it's very annoying. So anything I can do to make the files smaller, I do like to do. Here I'm grabbing pretty much all of the columns. I'm renaming the columns. You can do whatever you want here. I like to rename them so that they look very pretty and perfect. And so now we have subject, trial, time. Time starts at -1000. This is an intentional choice I made because I want 1000 milliseconds of data before the onset of my trial, the critical stimulus. And so that's what I've given myself. We have X and Y coordinates, which I am not going to analyze, but for some analysis methods, we'll talk about this afternoon. If you're using generalized additive mixed modeling, you can put your X and Y coordinates into your model. It will certainly count for some model variance. And if you are doing something complicated, like visual world paradigm, I mean, good luck to you, but you're going to need these X and Y coordinates. We have our pupil diameter, all of the information about this trial. Just a small note for those of us who are doing research here with Spanish, accents do not play nicely necessarily with some of the functions I used. So this is supposed to be the tras, and it's missing the A because it was accented. I know what it's supposed to be, so it's not a big deal. So I just sort of ignored it, but just a heads up. Okay, so we have a completed file. We want to save it. We're going to set our working directory to our output directory, save this file with our subject name. So I'm just creating a name for this file, which is customized. It'll be my subject ID, and I'm going to call it _compiled because it's the cleaned up pretty version of their data frame. So if you run this code chunk, it might take a second. Go to your Finder, or if you're on a PC, whatever it's called on a PC. I don't even know. Look what's appeared in this folder, our beautiful data set for participant 101. Wow, exciting stuff, right? Well, let's remind ourselves of something, which is that I told you at the beginning, we've been doing 3A through 3H. We purposefully entered this loop. We were only processing participant 101. And we were just going through step by step for learning purposes. But this is written to very efficiently process an entire directory on your folder, on your computer. So if we want to process all 5 of these people, maybe you have 100 people, you just want to run the whole thing, what you will run is the entire code chunk number 3. So if you are following along in the RMD, I, at the very bottom, after the "we're done" statement, have put the full code chunk 3 so that you can now you can click play, and it's going to run this as a for loop. And as this runs, we'll see messages start to appear on the bottom in just a moment. So we can see it's running the first participant. It tells us it finished 101, and it's going to go on to participant 2. And if you come to your compiled folder, you can watch the files magically appear. I did intentionally give you 5 files that are all good and don't have any crazy things. So they should just process without issue. I've actually had really good luck at BCBL. I don't know if it was just the eye tracker at my old institution was crazy and did crazy things, but I don't often have issues processing data. I think Daphne Weiss maybe had a couple of participants whose files got corrupted, but maybe that was actually converting from EDF to ASC. And I don't know if she's watching right now to chime in on that, but yeah, Daphne said she had 1. Yeah, so it's a rare occurrence that things go wrong, but it is good to know that there will be messages there to guide you when things do go wrong so that you don't feel crazy. So you can figure out, oh, this file is corrupted. It's not something I did, it's the file. Or alternatively, there's nothing wrong with my files, which is actually a nice thing because you want to keep your data, but there's nothing wrong with my files. I made a logical error, and you can figure out what went wrong there. This is finished, so it's done with participant 105. If we scroll up, this went so fast that you couldn't really see the messages, but it tells you when it starts working on a participant too. If you're running this on the server, it goes a lot slower, at least for me on Kahalo 4. So it won't, yeah. Hmm?
The processor is good. Just
Mm,
the one you have 2.4.
Interesting.
Yeah.
Yeah, I don't understand how servers work. I'm not gonna pretend that I do. Okay, mhm. Yeah. Okay, let me see if I have any wrap-up notes. We've looked at our files. Did things go well for people? I suppose I should check in. Thumbs up, that's great. So in sum, with this Pupillometry ASC compiler, what can we do? We can extract key information from EyeLink files, those messages, which are very critical. And this is what you need to keep in mind when you are building your experiment. And I highly recommend when you're building your experiment for the first time and you're coming up with the messages, look at your first pilot participant or handful of pilot participants, run this compiler because you will quickly find out if you're missing a critical message that you need. I do this every time and I often find something that I didn't think about. Like, for example, I was running an experiment where participants hear a sentence and they type what they heard. And I realized I was not sending the typed responses as a message to the file. Technically, that information is saved by CyclePy. And so I had redundant like CSV files, but I wanted it to be sent in my messages. So this is the really critical piece of advice, and the thing that we'll need customized for this script is your messages are always unique to your experiment. The timing information is probably going to be unique to your experiment. It's not going to be exactly the same as this example data set, which is why we're going to have a challenge where I'm going to give you a new data set and you have to figure out how to process it using this script. And hopefully it's the right amount of challenge and not too much amount of challenge. So we'll see how that goes. It's going to output CSV files in an R-friendly format, also an Excel-friendly format for further data processing. So we can even open one of these up. This file is going to be too big for Excel to open in its entirety. So it'll probably first be very slow, and then Excel will tell me, ooh, no. It'll show me like the first quarter of it. And it might be slow enough that I'm not going to wait actually. So we have a challenge because I recognize that this script does require an amount of customization, and this is a hard thing to learn. And so I want to prepare you as well as I can for being able to take the script and actually use it for your data set. So for this challenge, I want you to go to the R session 2 _ challenge folder. Just like for R session 2, you do have options. You can either use the R basic script or the R markdown script. You will see in these directories, there is the challenge file versus _answer key. So if we don't finish it and you don't have a chance to ask me what you did wrong, you can always go look at the answer key. We were working with this example data, and for the challenge, there is different data. It is a different experiment. There is information about the experiment that I provide for you. So these are 4 participants. So for example, yeah, I tell you some information about the timing here. If you're working in R basic, I tried my best to mark sections, edit me for challenge, so that you know that you don't need to edit the parts you don't need to edit. In R markdown, it's marked with this. So let me go ahead and open the R markdown. Yes. Mhm.
When I was compiling the participants, I got a warning gun
Mhm.
about, I don't know if you got it as well, sorry, I wasn't watching the screen, about NAs in some of the rows. So
Ooh.
is it like when they're blinking and so the data are not recorded, or?
Yeah, so this is a warning, not an error. And
I mean, the CSV has been created, I can open them.
mhm. Yeah, so this is interesting.
Because I don't know how it works with blinks, whether it replaces the coordinates and
With NAs.
with NAs and.
Yeah, this might be more than blinking though, because the thing is all files will have NAs from blinking. And so I'll poke into this. Apparently I did give you a weird file and I didn't even notice, but, yeah, expected 2 pieces. The other thing, so this is the warning from the EyeLinker package. So the EyeLinker package is assembling this enormous, oh wait, no, not you. What do I call it when I open it from EyeLinker? This data. We look at what EyeLinker opens, it's creating this list with all of these different layers. It is entirely possible that that warning is filling in NAs, not in our raw data even. It could be one of these other layers. So I'll poke around and see what I find. But it could be that in the SACODS file or something, there was some missing data and it just filled it in with NAs. But I doubt, because EyeLink automatically puts NAs when the pupil is missing already. So thanks for pointing that out. Okay, if you open up your R challenge file, I'm gonna sweep my environment. I like to do this just so I know there's nothing in there. We don't need it anymore. We're done with the previous data set. I just want to show you. Edit this code chunk for challenge data set is here. The reason, you'll see question marks. I tried where I could to replace things with question marks. So hopefully, if you get an error and it's like, there was a question, you know, like a question mark isn't an option, that's probably because you need to fill something in there. So let me know how it's going. I'm going to put up the information here. And also maybe I'll just read through the notes. So in this data set, the message for stimulus or sentence onset is audio_onset. So this is going to be the most critical timing information. The other thing is this data set does not have a duration for each trial. This is really frequent. Actually, I've done many pupillometry projects, and sometimes I send a message that this is the exact duration of my trial. And sometimes I just infer the end time of my trial from what I know about my stimuli, because I'm always collecting more data than I need. So I just need to decide where to cut it off, essentially. And this is one of those types of data sets. And that might be the case for your data set as well, which is why I wanted you to do this as an example. You only need to extract 5 critical messages. So it'll be your audio onset, the target audio, which is like the file name, accent. I'm doing research with accents. That's why there's accent here, counterbalance, and assignment, as in random assignment. Best of luck. I'm going to leave this up here so that you can see it and let you work in R. And if you want help, you can raise your hand. Marco.